Welcome to the world of atomic spectroscopy. Atomic spectroscopic methods are rapid, convenient, and usually of high selectivity. These methods can detect parts per million to parts per billion amount. The first step in all atomic spectroscopic procedure is atomization, a process in which a sample is volatilized and decomposed in such a way to produce gas phase atoms and ions. The first step in all with gas phase atoms or ions, there are no vibrational or rotational energy states. This absence means that only electronic transition occur. Thus, atomic emission, absorption, and fluorescence spectra are made up of a limited number of narrow spectral lines. The energy of emission typically is supplied by a plasma, a flame, a low pressure discharge, or by a high power laser. Before the external energy source is applied, the atoms are usually in the lowest energy or ground state. The applied energy then causes the atoms to be momentarily in high energy or excited state. The excited atoms then relax to the ground state, giving up their energy as photons of visible or ultraviolet radiation. A transition to or from the ground state is called a resonant transition, and the resulting spectral line is called a resonant line. Most measurements in AAS are made with instruments equipped with an ultraviolet visible grating monochromator. Radiation from the hollow cathode lamp is chopped and mechanically split into two beams, one which passes through the flame and the other around the flame. A half-silver mirror returns both beams to a single path by which they pass alternatively through the monochromator and to the detector. The signal processor then separates the AC signal generated by the chopped light source from the DC signal produced by the flame. The logarithm of the ratio of the reference and sample components of the AC signal is then computed and sent to a computer or readout device for display as absorbance. Background corrections, which includes deuterium lamp in which the hollow cathode lamp signal measures the total absorbance while the deuterium lamp signal provides an estimate of the background absorbance. The computer system calculates the difference and reports the background corrected absorbance. Second, during the high current pulse, a good estimate of the background absorbance is obtained. The instrument computer then calculates the difference, which is an estimate of atomic absorbance, the true analyte absorption. For Zeeman background correction, a magnetic field splits spectral lines that are normally of the same energy into components with different polarization characteristics. Analyte and background absorption can be separated because of their different magnetic and polarization behavior. Atomic or ionic emission from the plasma is separated into its constituent wavelength by the wavelength isolation device. This separation can take place in a monochromator, a polychromator, and a spectrograph. The isolated radiation is then converted into electrical signals by a single transducer, multiple transducer, or an array detector. The electrical signals are then processed and provided as input into the computer system. Despite its potential advantages of high sensitivity and selectivity, atomic fluorescence spectrometry has never been commercially successful. Difficulties can be attributed partly to the lack of reproducibility of the high-intensity source required and to the single element nature of AFS. Despite its potential advantages of high sensitivity and selectivity, atomic fluorescence spectrometry has never been commercially successful.